Good morning, students. In today's lecture, we want to look at a core concept in physiology. This is one of your early lectures in physiology, and therefore we need to explore this very core concept. And that refers to a word that you would have used or heard many times before, I'm sure, in high school, and that's the concept of homeostasis. Homeostasis. Now, homeostasis is almost the reason why the body exists. And as we'll see, almost all physiological processes in the body function to maintain homeostasis. But before we get into that, let me just begin by putting up a list of learning objectives. For those of you taking my course at the University of the West Indies, these guide what you need to do and what you need to know and how you'll be tested. For those of you listening elsewhere, these provide a nice little checklist for you to go over at the end of the lecture to make sure you've gained the necessary knowledge. I won't spend much time here because you can stop and look at these and write them down and do whatever you want with them. So let's just start with a little history. I think it's always useful to consider the history of how things were discovered and how concepts arose. And the first person to point us towards homeostasis is a French scientist, Claude Bernard, who lived in the 1800s. He made a statement. He said it in French, but I'm going to read it in English. He said the constancy of the internal environment is the condition for a free and independent life. And basically what he was saying is that as human beings, if we want to be able to be independent of our environment, meaning we want to move around in different environmental circumstances. So think of the situation you're experiencing right now. You're probably listening to this lecture in an air-conditioned room. But when you finish, you may step outside and you might go from a room in which the temperature is 18 degrees and step outside into sun that's 35 degrees. The thing that allows you to do that, the freedom that allows you to do that, is that something is regulating the internal environment of your body. And the first person to come up with that concept was this guy, Claude Bernard. The word homeostasis was actually coined by an American physiologist, Walter Cannon. And it's believed that he popularized the concept when he wrote a book called The Wisdom of the Body. And so Cannon is another person who's very much associated with the concept of homeostasis. So having looked a little bit at the history, and if you read about these men, you can find out how they came to these conclusions. Let's give a definition of homeostasis. So the definition of homeostasis that I would like us to use is that the dynamic maintenance of a relatively constant internal environment to create optimal functioning for the body. Let me repeat that. Homeostasis can be defined as the dynamic maintenance of a relatively constant internal environment to create optimal functioning for the body. And when we talk about the dynamic maintenance of an internal environment, what we're describing is there are a set of parameters or measures that define the internal environment of the body, and these have to be maintained. And I want you just to stop for a moment and think about, well, what parameters that exist on the inside of the human body are you aware of that need to be under homeostatic control? If you pause the slide and think about it and make a list, you should probably come up with parameters like blood oxygen levels or blood carbon dioxide levels. These are the blood gases. You might come up with glucose levels, amino acid levels. These are the nutrients that supply the body. You might come up with things like body temperature, certain hormone levels. All of these are examples of parameters that are under homeostatic control. Another one that's very interesting that people believe is under homeostatic control is weight. But then there are other parameters that are not under homeostatic control. A good example of that is height. Height is not under homeostatic control. So having given you this definition, let's look at some of the core concepts that are considered in that definition. And the first core concept is we're referring to the internal environment that's maintained in this state of dynamic balance. And I've already mentioned to you that the thing that allows you to go from a very cold room to a very warm outside environment, is because the inside of your body is maintained. So by maintaining a constant internal environment, it allows human beings to exist in many, many different external environments. And again, just think about persons living in the Arctic Circle, like Eskimos, and compare them to persons who live in the Saharan desert, like the Bedouin. Incredibly different environments, but a human physiology that operates to keep human beings alive in these different environments is exactly the same. And that physiology is homeostasis. The second key concept in our definition is dynamic. Homeostasis is a dynamic process. By that we mean it's not a static process. Things are always changing in the body, and the body is therefore always having to adapt. You see a little diagram there on your slide, and that diagram is a graph of how blood glucose concentration is changing with time. And what you'll notice is as you go throughout the day, your blood glucose concentration varies. But in order to keep that dynamic maintenance around a certain level, which we call the set point, the body releases certain hormones. So after you've eaten a meal and your blood glucose increases, the body releases insulin that reduces your blood glucose levels. But if your blood glucose then begins to fall too low, as you utilize the glucose throughout the day, the body can release another hormone, glucagon, which causes the insulin levels to rise. And this oscillation about the mean is what we call the dynamic maintenance. Balance here, therefore, does not mean unchanging, but it does mean keeping the parameter within the narrow confines of the set point that has been set for it by the body. And the last concept that I want you to understand is that of optimal functioning. There are a coded set of conditions in which the cells of your body function best. These have been coded by genetic programming, and these help create the set point for your body for all of these parameters. So there's a set point for blood glucose, there's a set point for blood oxygen, there's a set point for body temperature, which is the one we probably know best. I think all of us know that our body temperature set point in Fahrenheit is about 98.6. In Celsius is about 37 degrees. So the next question we must ask ourselves is, well, what systems has the body developed to help maintain homeostasis or regulate homeostasis? And there are two systems I just want to point you to. The first is called autoregulation, which refers to regulation taking place at a very localized level within the body, at a cellular level or a tissue level. And the second is extrinsic regulation, which is regulation that involves central control and primarily involves the activity of the nervous and the endocrine systems. Now, homeostasis is primarily associated with extrinsic regulation, but I do just want to mention autoregulation to you. Autoregulation is the activity of cells, tissues, or organs to automatically adjust to the environmental change. And it usually refers to changes in the diameter of blood vessels in response to changes in oxygen concentration or oxygen tension. So, for example, if the concentration of oxygen in the blood supplying the heart decreases, those blood vessels automatically detect this and dilate to ensure more blood and more oxygen comes towards the heart. And there are other organs that operate exactly like this. The kidney and the brain are all very good examples. So autoregulation operates at a very localized level and most often refers to changes in blood diameter to regulate the delivery of oxygen to tissues. Now, the one we know very well is extrinsic mechanisms. And extrinsic mechanisms are central processes in the body that regulate all of those parameters that I've been talking to you about. And if you have central mechanisms, you need a central structure that controls these things. And for many of the parameters of the body, those structures are found within the brain. And I just want to point out one structure that I want you to do a little bit of research on yourself, the hypothalamus. Very small structure in the brain, located close to the midbrain below the thalamus, but very key in homeostasis and controls many processes. So please just do a little bit of reading on the hypothalamus and begin to familiarize yourself with the hypothalamus. You will study the hypothalamus in a lot more detail later, but it's important as you begin to consider homeostasis and you begin your journey in medicine or the allied health sciences that you have an understanding of the hypothalamus and what it does. So the mechanisms that are used in homeostasis are feedback mechanisms. And we talk about two forms of feedback, negative feedback and positive feedback. Now, negative feedback is feedback that runs counter to the environmental change. And I have a little cartoon here to demonstrate that. You see a guy speeding down the road. He's going at 80 miles per hour. And he suddenly realizes, hold on, wait a minute. I'm in a 50 mile per hour zone. And he immediately slows down by applying pressure on the brakes. But then he overcompensates. And he slows down from 80 miles an hour to about 20 miles an hour. And he begins to cause traffic to pile up behind him. And that creates a lot of irritation for fellow drivers who begin to blow their horns and honk at him. And so he speeds up again. Negative feedback works very much like this. It's feedback that moves the parameter in the opposite direction to the environmental change. And so we want to consider, well, how does the body do this? How does the body set up these negative feedback systems? And to do that, it creates a negative feedback loop. Now, I want you to do a little exercise right now. I want you to pause this video. I want you to think about an air conditioning unit because they are pretty ubiquitous, meaning they're found in many places across the world. So you should be familiar with an air conditioning unit. And I want you to try and diagrammatically represent the components of an air conditioning unit that allow it to keep the room at a particular temperature. Whatever temperature you want, whether you set your air conditioning unit to 25 degrees Celsius or 18 degrees Celsius, how does this air conditioning unit work to produce that temperature? I'm not too interested in how the air conditioning unit cools the air. What I'm interested in you describing how the air conditioning unit maintains that temperature. So you can pause the video, you can do that, and you can come up with your diagram. Now, hopefully, you have come up with a diagram, something like this. This is a negative feedback loop. And for the negative feedback loop, the first thing you need is to establish the set point. For an air conditioned unit, that's the temperature that you want the room to be at. And you use your remote control device to set your temperature to, say, 20 degrees. Once you have set your temperature to 20 degrees, you need sensors in your environment that are measuring temperature. And the air conditioned unit has that. It has sensors. It has a thermostat that's measuring the temperature of the room. And then you need a comparator within the air conditioning unit that compares the set point with the sensor and creates what's an error signal. So you set your air conditioning unit to 20 degrees. The sensors detect that the room is actually 28 degrees. And so there's an error signal of plus 8 degrees. And that information is generated by the comparator. And that's sent to the controller or the effectors, who immediately activate a system to blow cool air into the room. In the case of an air conditioned unit, it activates the condenser. As that cool air is blown into the room, the sensors begin to notice that the temperature is dropping, and the error signal therefore gets smaller and smaller until the comparator notes that the set point and the sensors are equalized. And then you can literally hear the compressors turned off because the controller no longer needs to affect that cool air coming into the room. So that's a perfect example of a negative feedback loop. And again, this diagram summarizes exactly what we were just talking. Now, the important thing to note is negative feedback systems in the body work exactly like this. They work just like this. From this, we can see that negative feedback has certain features that limit its functionality. negative feedback is very, very good for adjusting and maintaining that dynamic balance. But there are some features that are not the best. Firstly, negative feedback control is initiated after the variable has been disturbed. So it's always in response to. Negative feedback is not proactive, it's a reactive form of feedback. Secondly, the amount of correction to be applied depends on the magnitude of the error signal, and that can lead to incomplete correction or overcorrection. Or as we saw a little bit earlier, there are oscillations about the mean, and therefore your variable is regulated, but it's not always where you want it to be. Now, to overcome this, the body often uses multiple regulatory mechanisms. As we saw with the issue of blood glucose, the body has one hormone to reduce blood glucose and another hormone to increase blood glucose. And that's very similar to the example of the car that I just told you about. The car has both an accelerator and a brake, and that gives you a lot more control over the speed of your vehicle. Think about the fact that if you just had a car and the only thing you had was an accelerator, that means in order to slow down, it would take you a lot longer, and therefore you have a lot less control over the car. But by having multiple regulatory mechanisms, you're able to overcome the disadvantages of negative feedback and tightly maintain the parameter you want within its particular range. So here's another diagram looking again at insulin, blood glucose, and glucagon, and just showing you how the multiple regulatory mechanisms in the body in a lot more detail are able to regulate blood glucose. I will let you look at this diagram and read it a little bit later. It basically says the same thing that we've been talking about throughout this lecture. Now, I want to give you a little bit of homework. One of the best studies examples of homeostasis is the regulation of body temperature. So I would like you to go and study the regulation of body temperature. How does the body maintain body temperature? What are the homeostatic control systems used to regulate body temperature? And now I want you to think about pathophysiology. What happens when the physiology goes wrong? So what is a fever? What are the symptoms of the fever? Why do we get those symptoms? What are the mechanisms responsible for the generation of a fever? And then the last thing I want you to do is look and find out, how do antipyretics work? Antipyretics are drugs or substances that reduce fever, and I want you to discover how they work. In doing this exercise, you're going to be able to practice and understand more about homeostasis and the things you've been studying in this lecture. Okay, so let's just talk briefly about positive feedback. Positive feedback, we talk about it now in contrast to negative feedback. It's not really used in the context of homeostasis, and it's not used often in the body, but it does have an important role at certain points. So whereas negative feedback gives you an error signal that reduces deviation from the reference points, positive feedback gives you an error signal that increases the deviation from the reference point, and you end up with what is called a vicious or a virtuous circle, depending upon if that is useful to you. So in nuclear reactors, you get a critical mass and you get a positive feedback cycle that is harnessed to produce energy. In the body, we use positive feedback when we want to produce very large changes very quickly. And so we have another cartoon that describes the activity of positive feedback. And I like to describe this as sometimes what happens in a house with a lot of young children like myself. The first one wakes up and they immediately wake up the others, and then they wake up the others, and in a very quick time the entire house is awoken. That's an example of positive feedback, as you can see in the little flow diagram on the slide. So positive feedback is a control in the direction in which the environmental variable is moving, and it leads to very rapid and very large changes in a particular parameter. The body doesn't use it often, but the body does use it in the process of childbirth. where there's a positive feedback interaction between the hormone oxytocin and the uterine muscle designed to push the baby out. And here again, you want to be able to have a quick delivery, and that's why you have a positive feedback cycle. Another example is in blood clotting, where you want to seal off the damaged capillaries, and that blood clotting mechanism utilizes a positive feedback cycle. And later on in this course, you will study another example of positive feedback in the action potential. So that's positive feedback. The next thing we're going to do is we're going to end
Today we are going to talk about a topic that is near and dear to our hearts, the cell membrane. But in order to be able to talk about this magnificent, powerful structure, we have to talk about a vocabulary word that is extremely important in order for this to work correctly. So we're going to talk about the word homeostasis first. The word homeostasis, it actually comes from a Greek root homeo, which means constant, and stasis, which means stable. So basically this word means stable, remaining the same. It's very, very important for cells to stay in a state of homeostasis, where they're staying stable. And not just cells, I mean, your entire human body has to stay in homeostasis. Let me give you a good example. Say you are outside and it is 20 degrees Fahrenheit. That's really, really cold. And you are freezing and you're in shorts, which was not a wise wardrobe choice. So what ends up happening is you start to shiver. Now, when you shiver, you don't really think you're doing much except this annoying shaking. But actually, whenever you shiver, your muscles are actually producing energy. They're producing heat for your body. And it actually does raise your body temperature slightly. It helps you regulate your body temperature, but you still often feel cold. Your body definitely would prefer you to move indoors where it is warm. Homeostasis is a way that your body, by using the shivering, can generate heat to try to maintain a stable body temperature of 98.6 degrees Fahrenheit. And of course, when you get really hot, what do? You sweat. You sweat, and all of the buckets of sweat that you produce helps you cool off. This is a way that your body remains in homeostasis all the time. It's trying to keep a constant temperature. Well, remember how I told you we're going to talk about something near and dear to our hearts? We're going to talk about the cell membrane. The cell membrane is so important for us in order to survive. Every single living cell, all cells, this is one of the very few times in biology where I'm actually going to say all living cells have a cell membrane. They don't always have a cell wall. That's a different thing. But they all have a cell membrane. Because you see, the cell membrane is the gatekeeper of everything. It controls what goes in and what goes out. And that might not seem like a big deal. But if you can't control your food coming in and your waste going out, you're going to have some problems. So the cell membrane controls this. And that's essential for keeping homeostasis. In fact, bacteria can be a good thing. There's a lot of ways bacteria are beneficial, but they can also be a very bad thing. Well, antibiotics kill bacteria, and one type of way that some antibiotics work is by piercing little holes in the cell membranes of the bacteria. And so what happens when you pierce little holes in the cell membranes of bacteria? Well, they can no longer keep homeostasis, and they will die. So homeostasis, extremely important word, cell membrane. Again, all living cells have it. It controls what goes in and out of the cell, and by doing so, it maintains stability. This is the Amoeba Sisters, and again, we're encouraging you to stay curious.
So I trust you have enjoyed this lecture, and I hope you now have a very good understanding of homeostasis as a core functional part of physiology and therefore medicine and allied health sciences. And I also hope you understand some of the mechanisms that the body utilizes to bring about homeostasis. In actual fact, everything that you study in medicine and allied health sciences will basically be describing the processes that the body utilizes to maintain homeostasis. And then when you begin to look at disease, you look at what's gone wrong in the body when homeostasis is no longer functioning. So until our next time together, goodbye and take care.